Presented is the problem for item number 1. Given for this problem is the height of the waterfall, which is 75 meters, volumetric flow rate of 105 cubic meters per hour, and the energy demand, which is 750 kilowatt hours per week. Required is the maximum power theoretically available from the waterfall, and is power enough to supply the demand. Since we need to determine the energy of an object with respect to its height, we will use potential energy as work. We'll plug in our values of gravity and height and convert volumetric flow rate into mass flow rate by multiplying it to the density of water and convert hours into seconds. Energy supplied will be 21,373.19 joules per second or watts. We need to convert the energy demand into watts so that we can compare it to the energy supplied. The converted energy demand is 4,464.29 watts, which is less than the energy supply. Therefore, the maximum theoretical work is sufficient enough to supply the demand of 750 kilowatt hours per week. Presented is the problem for item number 2. The given values for this problem is work, which is 16.95 kilojoules, volume of 85 liters, change in temperature 1.3 degrees Celsius, mass of water 2.27 kilograms, pressure 1.7 bar, and considering that our system is the air compressed in the large piston. Required for this problem is the change in the internal energy of air. The equation for the change in internal energy is delta U equals Q plus W. Since the change in temperature is subjected to the surroundings, delta U will become negative Q plus W. At constant pressure, Q is equals to mc delta T. By plugging in our values with the specific heat capacity of water, the answer will become 12.35 kilojoules. In plugging in our values of Q and W, the change in the internal energy of air is 4.6 kilojoules.
For problem number 3, we devise a reversible non-flow process by cooling the system to a constant volume and heating it to a constant pressure, which is shown by steps A and step B. For step A, we get T prime, which is the temperature when the system is cooled with constant volume, and using Gay-Lussac's law, we get T prime to be 29.315 Kelvin. Then we get the change of temperature for steps A and step B using this equation, which gives us these values. For constant volume, the change of internal energy is CV change of T, where CV is given to be 5 halves R. Then substituting this value, we get change of internal energy for step A to be negative 5484 joules. Next, we get V1 and V2 by using the ideal gas law. Then rearranging this equation and substituting the values, we get a value for V1 to be 2.437 times 10 to the power of negative 3 meters cubed. For V2, we do the same step to get us a value of 2.769 times 10 to the power of negative 2 meters cubed. For the change of enthalpy for step A, we use this equation and substitute the values to get about negative 1767.3 joules. For step B, for constant pressure, change of enthalpy for step B is equal to Cp change of Tb, where Cp is equal to 7 halves R. We substitute these values to get change of enthalpy for B to be 8841.65 joules. For the change of internal energy for step B, we rearrange this equation to give us a value of 6316.3 joules. For the total internal energy and enthalpy, we add each value from each step, then we get these values.
For problem number 4, we were asked to solve for the percentage of heat input to the heart converted to flow work. We are given 5 liters per minute as the average rate of the heart pumping blood. The blood pressure for venous side or intake is 0 millimeter mercury, and that on the arterial side or discharge is 100 millimeter mercury. It was mentioned in the problem that energy is supplied to the heart as heat released by the absorption of oxygen in the cardiac muscles. 5 milliliter oxygen gas per minute is absorbed, while 20.2 kilojoules is released per mole of oxygen gas absorbed. Begin by setting up your diagram and assumptions. In this case, we assume that the change in internal energy is negligible, no shaft work, and the fluid is incompressible, making the height and velocity differences negligible. Calculate for the energy supplied to the heart by multiplying energy absorption rate to the energy supply rate, we get 101 kilojoules per minute. Set up your general energy balance equation. We use the energy balance for steady state flow since the heart pumping blood is a steady state flow. We assume that height and velocity differences are negligible, so now we can cancel out the kinetic energy and potential energy terms. Divide both sides by the mass flow rate, giving us this equation. Transpose W to the other side, since our goal is to calculate the work requirement for heart to pump blood. Since we know that the change in enthalpy is equivalent to the internal energy plus the differential of pressure times volume, we can substitute it to the delta H term. We now have this. And since we know that internal energy minus heat is equivalent to work, and work is equivalent to the negative of the differential of pressure in terms of V, we have this. We can cancel out PdV term. We have W is equivalent to VdP. Integrating, we get work is equivalent to the volume times the change in pressure. Substituting values, we get 1.111 joules per second or 0.06666 kilojoules per minute. To calculate for efficiency, we get the ratio of work requirement for heart to pump blood and the total energy supplied times 100%. We get 0.066% efficiency.